Hello everyone, I am Harita and today I am going to present about quantum computing and quantum information. So let us begin with an introduction to quantum computing and the motivation behind quantum computing. Quantum computing uses the principles of quantum mechanics to process and store information. As we know, in classical computers, we use bits which can store the values of either 0 or 1. So unlike this, in quantum computers we use qubits or quantum bits which can exist in multiple states simultaneously. That is, they can store both 0 and 1 at the same time. So as you can see in this picture, let us suppose we have n classical bits. So each of these n bits will store either 0 or 1. So totally we'll have about 2 into 2 into 2 and so on till n. So we'll have 2 power n possible permutations. Out of these 2 power n possible permutations, at a single instance of time, only one possible permutation is being stored by n classical bits. But if we take quantum bits, then there are 2 power n possible permutations, but each bit can store both 0 and 1 at the same time. That means all of those 2 power n possible permutations can be stored simultaneously in n bits at the same time. So n qubits can exist in a superposition of all 2 power n combinations simultaneously. So for example, if we take 3 qubits, then each of these 3 qubits will store both 0 and 1. That means all possible 2 power 3, that is 8 possible permutations starting from 0 0 0 to 1 1 1. All of these possible permutations can be stored at the same time. But whereas in classical bits, out of these 2 power n, out of 8 permutation, any one, like 101, 10, 110, like any one out of these 8 permutations is only stored in classical bit at the time. So this was the main difference between classical bits and qubits. So this is the factor which can lead to exponentially fast computations compared to classical computing. Certain problems such as simulating quantum systems, especially factoring large numbers. Factoring large numbers is a principle used in cryptography. So and optimizing complex systems, these are computationally infeasible for classical machines, but these can be done feasibly and at a quicker rate using quantum computing. So as I said, the real power of qubits is in parallelism during computation. That means like these 2 power n possible permutations, they will exist simultaneously before measurement. So before measurement, during computation, all of these 2 power n possible permutations are seen at the same time. But once we measure, all these 2 power n possible permutations collapse to a single permutation, like the classical one. So but before we measure, during computation, quantum algorithms can see all these 2 power n possibilities at the same time, only before measuring. So let us look at some examples to get an idea at the speed gain when we use quantum computing. So first thing is Grover's algorithm, which is used in database search. So suppose we have a database consisting of n records, n items. So if we want to search, if we want to perform a search, then using classical computer we need about n steps to search n items. But using a quantum computer, we can do the same in only root n steps. So if we take a million items, 10 power 6 records, then classical takes about 10 power 6 steps, whereas quantum computing takes only square root of 10 power 6, which is 10 power 3, about 1000 steps. So from 1 million to 1000 we are able to reduce the number of steps. And one more important algorithm is the Shor's algorithm. Like one of the major issues we face in classical computing is factoring huge numbers. Suppose we take some 2 very large prime numbers and multiply them together. The multiplication is quick, we get the answer. But when we take a very huge number and try to factor it out as product of its primes, then that process is quite time consuming in classical computers. Like for example, a 2048 bit number would take about billions of years to factor it, but in using quantum computers we can do it in a matter of hours or days. So as we see that some problems like quantum computers increases the rate of solving the problem, but at the same time some problems which are computationally infeasible, like billions of years is infeasible. Some problems which were impossible to solve using classical computers can be solved using quantum computers. So and these have very impactful applications too. For example, factoring a number, this hardness of factoring a number is the principle behind RSA algorithm in cryptography. The RSA algorithm in cryptography relies on this hardness of factoring huge numbers to for data encryption, but using quantum computer we can override this hardness, we can do it easily or quickly. So new fields like post quantum cryptography are under emergence. So now let us look at qubits or the quantum bits, which are basic units of quantum information. So what is a qubit or a quantum bit? Physically it can be implemented by any quantum particle which has two distinct states, like photons. Photons can be either horizontally or vertically polarized, trapped ions, or superconducting circuits. We'll look at each one of them. So these physical implementations, they rely on quantum mechanical properties like superposition and entanglement. So let me briefly explain. Superposition means before measuring a quantum a quantum system, it exists in a state of superposition, that is simultaneously multiple states exist at the same time. Before measuring or before observing, we could not tell about the state of the quantum system. Only when we measure the multiple states, they collapse into a single state. So that was superposition. And entanglement means two quantum particles, no matter the distance between them, or no matter the external force or distance between them, two quantum particles, when they are said to be entangled, the change to one particle will immediately and automatically affect the other particle. So if we measure one particle, we can get to know about the state of the other particle. So they are they are entangled. So any whatever happens to one particle, the same thing it happens to the other particle, no matter by how much distance they are separated. So that was quantum entanglement. So now let us look at some of the physical realizations of qubits. So our first one is through superconducting qubits. So it is used in IBM and Google's quantum computers. So the concept behind this superconducting qubits is like special circuits are made with superconductors, with materials with tending to zero, absolute zero electrical resistance at very low temperatures. So microwave pulses, they control the state of the qubit, and but one very big challenge in the superconducting qubits is it needs very cold temperatures near absolute 0 Kelvin to function, to have the superconducting nature. And the main issue is not about the computation or processing. It's about maintaining this very low temperature. And coming to trapped ion qubits. Trapped ion qubits, like individual atoms or ions, are trapped in electromagnetic field, and we use lasers to manipulate the electronic state of these ions. Some of the companies which use trapped ion qubits are IonQ and Honeywell. So in trapped ion qubits, Based on the energy level of the ion, we can determine the quantum state. Like if it is in lower energy level, then it's 0, and if it's in a higher energy level, then it's in 1 state. And coming to quantum dots, quantum dots, we use the spin of the particle to determine the state. Spin down represents a 0 and spin up represents 1. And coming to photonic qubits, as I said, it depends on the polarization of the photon particle. So if it is horizontally polarized, it represents 0 state, and vertically polarized, it represents 1 state. And now let us look at the mathematical representation of qubits. Now we saw the physical realization of qubits. Now we are going to see how it is dealt with mathematically. So qubit is represented as psi, the state of a qubit, and it is equated to a column vector alpha beta. So here the first element alpha is a measure of how much the qubit is in 0 state, and the second element beta is the measure of how much the qubit is in 1 state. Sorry, there is a typo here. And if we take the amplitude square, like alpha is the probability amplitude, so if we take its magnitude square, then we get the probability of measuring the qubit in the state 0. And similarly, if we take the magnitude of beta whole square, we get the probability of measuring the qubit in state 1. So by normalization, the total probability must be 1. So magnitude of alpha square plus magnitude of beta square is equal to 1. And this psi, which is a column vector alpha beta, can be represented as alpha, which is a complex number, by the way, alpha scalar multiplied with the column vector 1 0 plus the scalar beta multiplied with the column vector 0 1. So this is writing it in this way is the direct notation. And as we saw, alpha is the probability amplitude of measuring it in 0 state, and beta is the probability amplitude of measuring it in 1 state. So if we want to represent a qubit having the value 0, then the probability amplitude of 0 will be 1, because it takes value 0. So alpha will be 1 and beta will be 0. And similarly, if the qubit takes value 1, then alpha will be 0, and beta, which is the probability of taking the value 0, it taking the value 1 will be 1. So we can represent any quantum state, any qubit, using a column vector alpha beta. So now once we have a column vector alpha beta, we can represent this qubit as a point on the surface of a sphere, which we call as the Bloch sphere. So here you can see alpha beta is a column vector. So if the vector is pointing perfectly vertical towards the north pole of the sphere, then that means the qubit is taking the value 0. And if it is pointing exactly opposite towards the south pole of the sphere vertically, then that means the qubit took the value 1. And in between any position, it means it is in a superposition of 0 and 1, with the probability being the respective coordinates alpha beta. So as there are logic gates in classical computers, similarly we have gates in quantum computers, which are the X, Y and Z gate. So these are nothing but rotating the column vector through pi radians or 180 degree along the respective axis. So applying X gate means rotating this vector. Remember, a vector is a representation of a quantum state, which is represented as a column vector alpha beta. So alpha is the probability, as you can see here. Alpha is the probability amplitude of it being in 0 state, and beta is the probability amplitude of it being in 1 state. So if we take any column vector, if we take any column vector and if we rotate it by 180 degree along the x-axis, that means we are applying the x gate to that quantum state. So similarly, we are taking a vector, and if we rotate it by 180 degree along the z axis, that means we are applying the z gate. And similarly, applying the y gate would imply taking a column vector and rotating it through 180 degree along the y axis. So as you can notice, if we take a vector and rotate it to 180 degree, then again apply the respective gate and again rotate it through 180 degree along the same axis, then we get our initial vector. That means in some sense, if we do the same operation once again, we get the initial vector. That means the x, y and z gates are in fact their own inverses. So we apply a gate to a vector, then we apply some other gate and we get the same vector back. So that some other gate is the inverse of the previous gate. So since if we apply the x gate to a vector and again we apply the same x gate, then we get the same vector back. So x vector is inverse to itself, and so on with the y and z. So these were about gates in qubits. Now let us look at it mathematically. What does it mean when we say we are rotating a vector by 180 degree? So we are applying a transformation on that vector, and a transformation can be encoded into a matrix. So here x matrix, it is this is the matrix 0 1 1 0. So it is made up of column vectors. So 0 1 is the coordinate where the initial standard basis vector will go to. So using this matrix, so when we multiply a matrix by a vector, we are actually applying a transformation to it. It goes to some other coordinate in space. We are actually transforming the space. We are either like squeezing or rotating or something. We are transforming the space in which the vector exists. So that can be done using matrices. So as I told, this rotation, it can be encoded into a matrix. So here x matrix is this 0 1 1 0. So when we multiply this transformation matrix to a vector, then we get the transformed version of the vector where the vector will land after the transformation. And similarly, we have the y matrix and the z matrix. Actually, rotation along the y axis is rotation in the plane of the sphere. So it is related to the phase of the vector. So that's why we have this component of I. And so this was about the mathematical representation of qubits. To summarize, a qubit can be represented as as using two numbers, alpha and beta. So we are putting them into a column vector, and alpha is how much the qubit is in 0 state, beta is how much the qubit is in 1 state. So if we take the magnitude and square them, we get the probability of measuring the qubit in the state 0. So according to normalization, the total probability should be 1. So magnitude of alpha square plus magnitude of beta square is equal to 1. And now we have a column vector for a quantum state. So this quantum state or qubit can be represented as a point on the surface of the Bloch sphere. And these are the XYZ 3 gates, and each gate is what it does is it rotates the vector by 180 degree along that particular axis, and each gate is its own inverse, because whenever we rotate a vector twice 180 degree, that means we are making a whole 360 degree turn, then it returns back to its initial position. And this rotation, this transformation can be encoded in a matrix, the transformation matrix. So these are the 3 XYZ matrices. So when we multiply a matrix by a vector, we are we get another vector which is the final position of that vector in the new transformed space. So this was all about the mathematical representation of qubits. Now let us move on to quantum programming languages. Like there are special libraries in classical programming languages or special new programming languages used to control quantum operations, manage qubits and define quantum algorithms. So some of the examples are Qiskit by IBM Quantum and Kuiper and QHash, which was developed by Microsoft, and Cirq, which was developed by Google Quantum AI. So let us conclude this presentation. Quantum computing can be extremely transformative. It can bring huge tides in technology, but it is an area still under research. So it is still in its early stage, but advancement in quantum algorithms can hold great promise for the future of fields such as cryptography, optimization and machine learning. So it can quantum mechanics not only improves the rate of problem solving, it can make impossible problems like which are impossible to solve classically. Quantum mechanics can make them possible. As I said, the example of factoring huge numbers, which is a basic principle in cryptography. So it can bring huge tides in such fields. However, there are certain challenges which we need to face, like qubit stability. So a system exhibits quantum behavior only for a very less very less period of time. So qubit stability, scalability, and as we already saw, superconductors require extremely low temperature, close to absolute zero. So these are some of the challenges in quantum computing, which are required to be overcome in order to unlock the full potential of quantum computing. Thank you.